The engine room of the SS William Harrison was a cathedral of noise and heat, a space where sound became physical pressure that crushed thought, and where every surface radiated warmth from steam pipes and machinery that had been running continuously for 9 days since leaving Halifax, and Chief Engineer Thomas Mackenzie stood before the main pressure gauge watching the needle hover at 220 pounds per square inch, the maximum rated pressure for the triple expansion steam engine that drove the single propeller shaft turning somewhere beneath his feet in the cold Atlantic water. And he knew with absolute certainty that this number, this safe conservative limit designed by engineers who'd never been chased by submarines, was going to kill everyone aboard. Above him, separated by steel decks and cargo holds filled with aviation fuel and ammunition and food meant for Britain, the convoy of 43 merchant ships plodded eastward at 11 knots, maintaining formation discipline that made them predictable targets, maintaining spacing that made individual ships vulnerable, maintaining speed that assumed destroyer escorts would provide protection, but those escorts were spread thin tonight and radio chatter suggested U-boats were gathering, suggested wolf pack tactics were being employed, suggested the mathematics of convoy defense were about to fail for another group of merchant sailors who'd done everything doctrine required and who would die anyway because doctrine assumed conditions that no longer existed. The explosion came at 2,140 hours, a muffled thump that Mackenzie felt through the deck plating before he heard it through the engine noise, and he knew immediately what it meant because every merchant sailor in the Atlantic knew that sound, had heard it in nightmares, had imagined it during every watch. A torpedo strike, another ship dying, another crew abandoning vessel if they were lucky or going down with their ship if they weren't. And the questions that followed were always the same: how close, how many U-boats, whether the escorts could respond, whether the convoy would scatter or maintain formation, whether tonight was the night when the odds caught up and the William Harrison joined the thousands of other vessels at the bottom of the Atlantic. Mackenzie checked the shaft revolution counter, confirmed they were making 76 revolutions per minute, which translated to roughly 11 knots through water, confirmed that this speed was exactly what regulations prescribed and exactly what would get them killed if U-boats were positioning for additional attacks, and he made a decision that violated every operating manual and every safety regulation and every conservative principle that peacetime engineering followed. He was going to push the boilers beyond their rated limits, was going to increase steam pressure beyond what the manufacturer recommended, was going to run this machinery harder than it was designed to run, and he was going to do it because following the rules meant maintaining predictable speed that made torpedo solutions easy, while breaking the rules meant maybe, just maybe, being somewhere else when torpedoes arrived at where calculations said his ship should be. The Battle of the Atlantic in 1942 was being lost through arithmetic that didn't require complex analysis. German U-boats were sinking Allied merchant ships faster than shipyards could replace them, were destroying tonnage that carried food and fuel and munitions that Britain needed to survive, were killing merchant sailors at rates that exceeded sustainable losses, and this attrition threatened to sever the maritime supply line that connected North America to Britain and without which Britain couldn't continue fighting, couldn't feed its population, couldn't equip its military, couldn't sustain operations that required resources the island nation didn't possess domestically. The U-boats operated with tactical advantages that made convoy defense desperately difficult. They could submerge to avoid detection, could attack at night when visual observation was impossible, could coordinate in wolf packs that overwhelmed escort defenses, could choose when and where to engage while escorts could only react to attacks that had already begun. And German Naval Command understood that they didn't need to invade Britain if they could starve Britain, didn't need to defeat the Royal Navy if they could sink the merchant fleet, didn't need dramatic victories if they could achieve strategic success through sustained attrition, and the numbers through early 1942 suggested the strategy was working, suggested that U-boats were winning the tonnage war, suggested that Allied merchant shipping was being destroyed faster than it could be protected or replaced, and this mathematical reality created existential threat to Allied war effort because modern industrial warfare required logistics and logistics required ships, and ships were being sunk in numbers that threatened to make continued operations impossible. The merchant vessels being sunk were not warships, were not designed for combat, were not equipped to defend themselves effectively, were simply cargo carriers that had been pressed into service moving military supplies and civilian necessities across an ocean that had become contested rather than controlled, and their vulnerability came from fundamental characteristics that peacetime design had never anticipated. They were slow because cargo capacity mattered more than speed. They were predictable because convoy doctrine required formation discipline. They sailed known routes because geography limited options, and they couldn't maneuver aggressively because their cargoes and their machinery weren't designed for violent evasion. and these characteristics that made them excellent peacetime merchantmen made them vulnerable wartime targets, made them easier to find and easier to hit and easier to sink than warships that were built and equipped for combat. The Liberty Ship program represented American industrial response to the merchant shipping crisis, represented recognition that building ships faster than they could be sunk was prerequisite for Allied victory, represented acceptance that perfect ships built slowly were less valuable than adequate ships built quickly, and the Liberty ship design reflected this priority. They were simple welded steel cargo vessels built using mass production techniques borrowed from automotive manufacturing, built using standardized components that could be fabricated at multiple locations, built using assembly line methods that reduced construction time from months to weeks to eventually days, built using designs that prioritized ease of construction over performance or elegance, and the result was a ship that was slow, maximum speed around 11 knots, and basic and utilitarian but which could be produced in numbers that eventually exceeded sinking rates and which could carry enough cargo to make each completed voyage strategically meaningful. The propulsion system that drove Liberty ships was deliberately conservative. A triple expansion steam engine that used steam pressure to drive pistons in 3 sequential cylinders of increasing size, extracting energy from steam as it expanded and cooled, driving a crankshaft that turned a single propeller shaft, producing roughly 2,500 horsepower that moved 14,000 tons of ship and cargo through water at speeds that would have been considered slow even for peacetime cargo operations. And this machinery was chosen not because it was modern, more efficient steam turbines existed, but because it was proven and simple and could be manufactured by companies with no shipbuilding experience, could be operated by crews with minimal training, could be maintained with basic tools and standard parts. And this operational simplicity mattered more than performance because Liberty ships needed to work reliably with whatever crews could be assembled rather than requiring specialists who didn't exist in sufficient numbers. The design philosophy assumed that Liberty ships would operate in convoys protected by naval escorts, assumed that speed didn't matter because convoys moved at the speed of the slowest vessel anyway, assumed that losses would occur but would be acceptable if overall tonnage delivered exceeded tonnage sunk. And these assumptions were pragmatic responses to wartime constraints, but they created operational realities where individual ships had little agency over their survival, where merchant crews could only follow convoy discipline and hope escorts prevented attacks and accept that sometimes they'd be unlucky, and this passivity, this acceptance that survival was statistical rather than something crews could influence through skill or effort, was psychologically difficult for men whose lives depended on outcomes they couldn't control. Thomas Mackenzie had come to merchant service from civilian power generation, had spent pre-war years operating steam plants that provided electricity to industrial facilities, had developed intuitive understanding of how steam systems behaved under various loads and how far machinery could be pushed beyond rated limits without catastrophic failure, and this experience had taught him that engineering specifications included safety margins, included conservative assumptions about maintenance and operating conditions and operator skill, included buffers between normal operating parameters and actual failure points, and these margins existed for good reasons, to account for wear and manufacturing variations and operator error and unexpected conditions. But they also meant that rated limits weren't hard boundaries beyond which immediate failure occurred, but rather were conservative operating points chosen to ensure reliability over extended service life under varied conditions. Mackenzie's frustration aboard the William Harrison stemmed from knowing that the triple expansion engine could produce more power than regulations allowed, could operate at higher steam pressures than peacetime specifications prescribed, could push the ship to speeds that would improve survival odds, but regulations written by people who weren't being chased by submarines forbade exceeding rated parameters, forbade the kind of aggressive operation that might save ships, and this regulatory conservatism made sense for peacetime where exceeding limits risked expensive breakdowns and where speed wasn't worth the maintenance costs, but made less sense for wartime where the alternative to pushing machinery was dying, where breakdowns could be repaired if you survived but sinking was permanent, where arriving damaged was infinitely preferable to not arriving at all, and Mackenzie understood this calculus even though regulations didn't acknowledge it, understood that wartime changed the risk-benefit equation in ways that peacetime rules didn't account for. The regulations governing Liberty ship boiler operations specified maximum steam pressure of 220 psi, specified this limit to ensure boiler safety and to prevent overstressing machinery and to maintain reliability over the ship's service life, and these regulations were enforced through official operating procedures and through chief engineer accountability, and through the understanding that exceeding limits meant official censure if discovered. meant potential criminal charges if equipment failure resulted in casualties, meant that engineers who pushed machinery beyond rated parameters were assuming personal liability for outcomes that couldn't be predicted, and this liability created powerful incentive for conservative operation, created culture where following regulations insulated engineers from blame while exceeding regulations exposed them to punishment, and so the rational bureaucratic response was to operate within limits regardless of tactical situation, was to prioritize career preservation over tactical advantage, was to let convoy commodores and destroyer escorts worry about survival while engineers focused on maintaining machinery within approved parameters. But Mackenzie understood that these rules existed because peacetime engineering prioritized different values than wartime operations required, understood that safety margins designed for 30-year service life didn't matter if the ship was going to be sunk in the next 3 hours, understood that boiler explosions were terrible but torpedo strikes were certain, understood that regulations reflected institutional caution that was appropriate for peacetime but potentially fatal in combat, and he understood that following rules would let him write reports explaining why he'd done everything correctly even though his ship sank, while breaking rules might save the ship but would require explaining why he'd violated regulations, and this asymmetry, where following rules absolved responsibility regardless of outcome while breaking rules created liability, was exactly backwards for wartime where survival mattered more than procedural compliance, and Mackenzie decided that he'd rather explain why he'd exceeded pressure limits than die following them. The technique Mackenzie employed to increase steam pressure wasn't dramatic or complicated, didn't require extensive modifications or specialized knowledge, just required understanding how the system worked and being willing to adjust parameters that regulations said shouldn't be adjusted. He increased boiler firing rates slightly, added more fuel to fireboxes to generate more heat, which increased steam generation, which increased pressure in the boiler drums, and he adjusted safety valves, the mechanical devices designed to vent excess pressure automatically, to allow higher pressures before they opened, adjusted them by tightening springs or adding shims or making small modifications that delayed their activation, and these adjustments were reversible and left no obvious evidence and could be explained as maintenance if questioned, and the result was steam pressure climbing from 220 psi to 235 psi and then to 250 psi, climbing into territory that manufacturer specifications said was inadvisable, climbing to levels that increased stress on boiler tubes and engine components, climbing to pressures that produced more power and turned the shaft faster and pushed the ship through water at speeds that regulations said shouldn't be attempted but which tactical necessity demanded. The ship's speed increased from 11 knots to 12 and then to 13, gained speed that seemed insignificant, just 2 knots, just 2 nautical miles per hour, but which changed geometry of torpedo intercepts, changed timing of attacks, changed whether the ship would be where U-boat captains calculated it should be, and this marginal advantage compounded over hours as the distance traveled diverged from what convoy speed predicted, as the ship's position became less certain, as torpedo solutions became less reliable, and Mackenzie watched the pressure gauges and listened to the machinery and felt the increased vibration that came from pushing everything harder, and he calculated that the risk of mechanical failure was acceptable compared to the certainty of dying at convoy speed. Calculated that boiler tubes might fail but could possibly be patched while torpedo strikes couldn't be repaired. Calculated that he was trading long-term reliability for short-term survival and that this trade made sense when long-term didn't matter if you didn't survive short-term. The U-boat that had torpedoed the convoy's trailing ship was part of a wolf pack that had been tracking the convoy since afternoon, had been coordinating through radio communications that Allied intelligence was intercepting but couldn't decrypt quickly enough to matter tactically, had been positioning for night surface attacks that would exploit darkness and convoy predictability, and the first torpedo strike was reconnaissance as much as attack, was designed to force the convoy to react, to reveal escort positions, to create confusion that would expose other targets. And the U-boat captain knew from experience that merchant ships in convoy maintained rigid formation discipline, maintained predictable spacing and speed, maintained courses that could be calculated hours in advance, and this predictability made torpedo solutions straightforward because if you knew where a ship was now and what speed and course it maintained, you could calculate where it would be in 20 minutes when your torpedo arrived, and the mathematics were simple geometry, were equations that U-boat crews drilled until they could solve them in seconds, were calculations that worked reliably when targets behaved predictably, and the convoy's response to the first attack followed established doctrine. Escorts raced toward the last known U-boat position, convoy maintained formation and speed, merchant ships continued plodding eastward because scattering made individual ships more vulnerable while maintaining formation preserved collective defense, and this doctrine made sense under conditions where escorts could provide protection but became questionable when escorts were overwhelmed or out of position or insufficient in number. And tonight the escorts were spread thin, protecting 43 merchants against multiple U-boats, and the mathematics didn't favor the defenders. The order to scatter came at 2,300 hours when radar contact suggested multiple U-boats converging, and when the convoy commodore recognized that maintaining formation would result in multiple ships being sunk before escorts could respond. And scattering meant each ship became responsible for its own survival, meant speed and maneuverability mattered more than formation discipline, meant captains could choose their own courses and speeds rather than conforming to convoy requirements. And for the William Harrison, this meant Mackenzie could push the machinery as hard as he dared without worrying about maintaining formation speed, could run the boilers at whatever pressure he thought the system could handle, could prioritize survival over regulations, and he pushed pressure to 270 psi, 50 pounds beyond rated maximum, and felt the ship respond, felt the shaft rotation increase, felt the hull vibrate in new ways, watched the speed indicator climb toward 14 knots, which was faster than Liberty ships were supposed to run, faster than the designer had intended, faster than peacetime operations would allow, but faster meant being somewhere else when torpedoes arrived, meant U-boat calculations being wrong, meant maybe surviving the night, and Mackenzie accepted the risks because the alternative was dying at regulation speed while following rules that assumed conditions that didn't exist in the North Atlantic in 1942. The night that followed was 3,000 miles compressed into 12 hours, was sustained high-output operation that pushed every component beyond its design envelope, was continuous vigilance watching for signs of impending failure. Unusual vibrations, pressure fluctuations, temperature increases, bearing noises, was maintenance crews working through the night making adjustments and tightening fittings and monitoring systems that were operating outside normal parameters. Was the entire engineering department understanding without explicit discussion that they were breaking rules, and that they couldn't acknowledge breaking rules but that survival depended on continuing to break them, and this unspoken conspiracy extended throughout the ship as deck officers noticed the increased speed and said nothing, as the captain understood his engineers were exceeding limits and chose not to investigate, as everyone aboard recognized that official policy and survival requirements had diverged and that prioritizing policy over survival would be insane. And so the William Harrison ran hard through the night while U-boats searched for targets that were where calculations said they should be and found empty water because the calculations assumed 11 knots and the William Harrison was making 14, and those 3 knots meant 3 additional nautical miles per hour meant after 4 hours the ship was 12 miles from where it should have been, and U-boat torpedo solutions that would have been perfect hits found nothing because the target wasn't where mathematics predicted. The engineering challenge of sustained high-pressure operation wasn't preventing single catastrophic failure, but managing accumulated stress across systems that were interconnected and where failure in one component could cascade. High steam pressure stressed boiler tubes that could develop leaks or fail completely if pushed too far, stressed engine components that wore faster under higher loads, stressed bearings that generated more heat and required more frequent lubrication, stressed the shaft and propeller that were transmitting more power than they were designed to handle, stressed electrical generators that were producing more current to support increased pumping and ventilation, and all of these stresses accumulated over hours and days in ways that were difficult to predict because machinery behavior under sustained overload wasn't well documented, wasn't something manufacturers tested, wasn't something operating manuals addressed because operating manuals assumed people would follow limits rather than deliberately exceeding them. Mackenzie and his crew managed these stresses through constant monitoring and preemptive maintenance, through watching for early warning signs and addressing problems before they became failures, through understanding that they were trading long-term reliability for short-term performance, and that this trade required accepting increased maintenance burden and accepting that components might fail in ways that wouldn't happen during normal operation, and they succeeded not through dramatic interventions but through unglamorous attention to details, through checking bearing temperatures every hour, through monitoring steam pressure continuously, through listening for changes in machinery noise that indicated developing problems, through maintaining cooling water flow and lubrication and all the routine tasks that kept machinery functional. And this success was earned through expertise and vigilance rather than through luck, was professional competence applied under difficult circumstances rather than miracle, was what engineering actually was when stripped of romanticism. Constant attention preventing failures rather than heroic responses to crises. The knowledge about exceeding boiler pressure spread through merchant marine engineering community through informal networks rather than official channels. spread through conversations in ports where engineers compared notes, spread through radio communications where coded language discussed efficiency improvements and performance optimization, without explicitly acknowledging that regulations were being violated, spread through the understanding that official policy and operational reality had diverged, and that everyone was pretending not to notice this divergence because noticing would require either changing policy or enforcing policy, and neither option was attractive to people responsible for winning the war. Officers pretended not to notice that ships were making speeds that should have been impossible at rated boiler pressure, pretended not to understand that engineers were exceeding limits, chose to not investigate because investigating would force acknowledgement and acknowledgement would require action, and action would either mean approving violations, which would create liability if failures occurred, or prohibiting violations, which would reduce ship survival rates. And both options were worse than maintaining plausible deniability, where officers could claim they didn't know details while engineers could claim they were just maintaining efficiency. The Admiralty remained officially unaware of the practice or chose to look away because the mathematics were compelling. Ships running faster had better survival rates. Better survival rates meant more cargo delivered. More cargo delivered meant sustained operations, and if this required tacitly accepting that engineers were exceeding regulatory limits, then that was preferable to losing ships through strict regulatory compliance. And this pragmatic calculation represented wartime thinking, where outcomes mattered more than procedures, where survival trumped doctrine, where winning required tolerating deviations from peacetime standards. And the fact that no official acknowledgement existed meant no official permission existed, but also meant no official prohibition existed, meant engineers who pushed machinery could claim they were simply maintaining their ships efficiently while officials who knew better could claim they didn't know specifics. And this mutual fiction allowed the practice to continue while maintaining bureaucratic cover for everyone involved. The impact of marginal speed increases across the merchant fleet accumulated into strategic effects that were difficult to quantify precisely but were certainly significant. Ships making 13 or 14 knots instead of 11 knots spent less time exposed to U-boat threat, covered convoy routes faster, presented harder targeting problems, forced U-boats to travel farther to intercept, which consumed their limited fuel, changed the mathematics of wolf-pack tactics because coordinating attacks on faster-moving targets was harder, reduced the time available for U-boats to position between convoys, and these effects compounded as multiple ships adopted higher operating speeds because U-boat captains couldn't simply adjust their calculations because they didn't know which ships were running fast and which were running at regulation speed, couldn't predict which targeting solutions would work and which would fail, couldn't maintain the certainty that had made merchant shipping such vulnerable targets, and this uncertainty degraded U-boat effectiveness even when individual attacks still succeeded because success rates dropped and attacks took longer to set up and more torpedoes were wasted on empty water where ships should have been but weren't, and gradually the tonnage equation began shifting as fewer merchants were sunk and as more cargo was delivered and as U-boat effectiveness degraded not through any single factor but through accumulation of marginal advantages that Allied forces developed through learning and adaptation and tactical evolution. The turning of the Atlantic War resulted from multiple factors reinforcing each other. Improved radar allowed escorts to detect surfaced U-boats. Increased escort numbers provided better convoy protection. Hunter-killer groups actively pursued U-boats rather than waiting for them to attack. Air coverage extended farther into mid-Atlantic, closing the air gap where U-boats had operated with impunity. Intelligence improvements allowed routing convoys away from known U-boat concentrations. And merchant ships running faster than regulations prescribed, and none of these factors alone was decisive, but together they shifted the balance from German advantage to Allied advantage, shifted the tonnage war from unsustainable losses to acceptable attrition, shifted strategic momentum from Germany strangling Allied logistics to Allies sustaining operations that would eventually overwhelm German defenses, and the merchant engineers who'd pushed their machinery beyond rated limits contributed to this shift, even though their contribution was never officially acknowledged. Even though no medals were awarded for exceeding boiler pressure, even though the practice remained technically illegal and officially unknown throughout the war. After the war ended and merchant ships returned to peacetime operations, the regulations that had been quietly violated were quietly restored. The boiler pressure limits were reestablished. The practice of running machinery beyond rated parameters disappeared as operating conditions changed, and as the urgency that had justified risk-taking no longer existed, and the engineers who'd done it went back to following manufacturers' specifications and operating within approved limits, and nobody discussed what had happened during the war because discussing it would require acknowledging that rules had been broken and that official policy had been ignored and that survival had sometimes required doing what regulations prohibited. And this silence was comfortable for everyone because it avoided uncomfortable questions about authority and compliance and whether following orders was always appropriate, avoided debates about when rules should be broken and who should make those decisions, avoided acknowledging that institutional regulations sometimes lagged tactical reality, and that people on the ground sometimes understood situations better than people writing policies. And so the practice was forgotten officially while being remembered personally by engineers who'd done it, who carried the knowledge that they'd exceeded limits and survived, who understood that regulations were guidelines rather than absolute boundaries, who'd learned that expertise sometimes meant knowing when rules no longer applied, and this knowledge shaped their post-war careers in ways they didn't discuss but which affected how they approached problems and how they thought about risk and compliance and the relationship between authority and effectiveness. Thomas Mackenzie returned to civilian power generation after the war, worked another 30 years operating steam plants, never exceeded rated boiler pressure again because civilian operations didn't justify the risks, never told anyone except his wife about pushing the William Harrison's machinery beyond limits, never sought recognition for doing what circumstances required, and when he retired and when people asked about his war service, he described it as routine merchant marine work, described it as manning the engines on cargo runs across the Atlantic, described it as unglamorous duty that had to be done but which wasn't particularly interesting, and this modesty wasn't false humility but reflected his genuine understanding that what he'd done wasn't heroic but was simply competent engineering applied under difficult circumstances, was recognizing when rules needed to be broken and breaking them carefully, was managing risk rather than avoiding it, was understanding that survival sometimes required exceeding design limits and that exceeding limits successfully required expertise and vigilance and acceptance that failures might occur, and he'd been fortunate that failures hadn't occurred, fortunate that the boiler tubes had held and that the shaft hadn't twisted and that the bearings hadn't seized, fortunate that mechanical tolerances had been sufficient to handle the stress, fortunate that his ship had delivered its cargo and that his crew had survived and that the war had been won partly because enough ships like his had made it across enough times that the logistics equation had favored the Allies, and this fortune wasn't luck but was probability, was understanding that pushing limits increased risk but that the increased risk was acceptable compared to the certain risk of following limits that were designed for different conditions, was calculating that mechanical failure was possible while torpedo strike was probable and choosing to optimize against the greater threat, was engineering judgment applied to wartime conditions where the calculus of acceptable risk was different than peacetime engineering assumed. The Liberty ship SS William Harrison made 17 successful Atlantic crossings during World War II, delivered thousands of tons of cargo to British ports, survived the war intact, was sold for scrap in 1947 when peacetime economics made maintaining aging steam-powered cargo ships uneconomical, and no monument marks its existence, no plaque commemorates its service, no museum preserves its machinery, and the ship exists now only in official records that list construction date and tonnage and final disposition, records that don't mention the night in 1942 when its chief engineer pushed boiler pressure to 270 psi and ran the ship at 14 knots while U-boats searched for a target that wasn't where calculations predicted, records that don't capture the thousands of similar nights when merchant engineers across hundreds of ships made similar decisions to exceed limits and push machinery and risk mechanical failure because the alternative was worse, records that reduce complex human decisions and technical challenges and survival calculations to bureaucratic data about ships built and ships sunk and tonnage delivered, and perhaps this reduction is appropriate because wars aren't won through individual heroics but through accumulated competence, aren't won through dramatic gestures but through unglamorous persistence, aren't won through perfection but through adequate performance sustained over time, and the Liberty ships represented this kind of victory, weren't elegant vessels, weren't particularly fast or capable, weren't ships that peacetime economics would have produced, but were adequate to the task they were built for, were producible in numbers that mattered, were reliable enough to deliver cargo if operated competently, and when operated by engineers who understood when rules needed bending and how far they could be bent safely, these adequate ships accomplished what they needed to accomplish, which was sustaining Allied logistics across an ocean, contested by submarines until Allied forces could develop the capabilities that would win the tonnage war and secure the Atlantic and enable the operations that would ultimately defeat Germany. And in this accomplishment, the William Harrison and thousands of ships like it justified their existence, validated the emergency shipbuilding program that created them, demonstrated that industrial production combined with technical competence could overcome tactical disadvantages, and proved that wars are won not by perfect machines operated according to perfect procedures but by imperfect machines operated by people who understand that sometimes, when survival requires it, the rules that assume normal conditions no longer apply and following them becomes more dangerous than breaking them, and having the judgment to recognize those moments and the expertise to break rules successfully and the courage to accept responsibility for outcomes that can't be guaranteed is what separates engineering from mere technical competence, is what allowed merchant marine engineers to contribute to Allied victory through actions that were never officially acknowledged and which they never sought credit for because they understood they'd simply done their jobs under difficult circumstances, had applied expertise to problems that required solutions, had survived conditions that killed many others, and had delivered their ships and their cargoes and their crews to destinations that needed them, and that this accomplishment required no additional recognition beyond the simple fact that they'd done it, that the cargoes had arrived, that the war had been sustained, that victory had been possible because logistics had worked, and logistics had worked partly because engineers had understood that maximizing boiler pressure beyond rated limits was less dangerous than maintaining regulation speed while submarines calculated intercepts, and this understanding, this recognition that survival sometimes requires calculated risk rather than procedure compliance, was the kind of wisdom that doesn't fit in regulations and can't be taught in manuals but which separates people who understand their systems deeply from people who only know how to follow procedures, and the war was not won by perfect machines operating perfectly within design parameters but by imperfect men who knew when the rules no longer applied and who had the competence to survive breaking them and who returned afterward to following those same rules because conditions had changed back to where the rules made sense again, and this flexibility, this ability to recognize when context changed the calculus of acceptable risk, was perhaps more important than any single technical capability, was the kind of adaptive thinking that industrial warfare rewarded, was what allowed Allied forces to learn and improve and overcome initial disadvantages. And while the boiler pressure trick was small part of this larger adaptive success, it represented the principle that would ultimately determine the war's outcome. That rigid adherence to doctrine designed for different circumstances was fatal while intelligent adaptation to actual conditions enabled survival, and the engineers who pushed their Liberty ships beyond design limits understood this principle in practical terms, even if they never articulated it theoretically, understood it through direct experience where following rules meant dying while breaking rules carefully meant possibly surviving, and they chose survival and they chose correctly and they contributed to victory through this choice even though their contribution was never officially recognized because it couldn't be officially acknowledged because acknowledging it would require admitting that regulations had been systematically violated and that this violation had been necessary and that official procedures had been inadequate for wartime conditions, and maintaining the fiction that everything had been done according to regulations was more comfortable than confronting the uncomfortable truth that sometimes winning required doing what peacetime thinking called dangerous and what regulations prohibited and what would have resulted in prosecution if discovered but which circumstances made necessary and which competent engineers could accomplish safely enough that the risks were acceptable compared to alternatives. And so the official history records Liberty ships delivering cargo at regulation speeds while the unofficial reality was that survival often required exceeding those speeds, and that the engineers who made this possible did so quietly without seeking recognition and without leaving evidence and without discussing it afterward because they understood that some things were done because they needed doing regardless of what regulations said, and that doing them successfully was its own reward and its own justification, and that no additional recognition was necessary or appropriate or desired.